SwayamPrabha. Digital India. Educated India.
Hello everyone, welcome to lecture 20, and we are going to discuss today what is called extension-torsion-inflation in a hollow cylinder. So, I will tell you what does each of the three things mean: extension, torsion, inflation. Okay. So, think of a cylinder. So, we have got a cylinder here. And suppose we are applying axial force to the cylinder. Okay. So, we could apply that by applying some traction at the two end cross sections, right. So, when you apply this axial force, the cylinder gets pulled, right. So, think of this cylinder and we are applying axial force at the two cross sections, two end cross sections. So, when you do that, the cylinder gets stressed, right. So, that is called extension of the cylinder. Due to axial force, the cylinder is getting stressed. You could also apply what is called torsion. No, so, if you hold the two ends and rotate it in two different directions, then you insert some twist in the cylinder. The different cross sections of the cylinder, they will rotate by different values and there will be twist inserted in the cylinder. So, that is called torsion. Okay. And inflation would mean, suppose the cylinder is hollow and you pressurize the cylinder from within. So, due to pressurizing it from within, the radius of the cylinder is going to change, right. So, that is called inflation of the cylinder. Think of a balloon, for example. When you fill air in the balloon with your mouth, the balloon gets inflated. So, that is called inflation. Okay. So, in case of cylinder, inflation would mean the radius of the cylinder changes, all right. Okay. So, coming back to the picture, if the cylinder is hollow, for example, so it will also have the inner wall, right. And then you would be applying pressure within the inner cavity of the cylinder to inflate it. So, there will be some pressure in this red region, internal pressure. So, you see that this pressure acts on the inner surface of the cylinder. So, it acts on the inner surface of the cylinder. One can actually also apply the pressure on the outer surface of the cylinder, but let us in this example focus on the case where we are only pressurizing it from within. Okay. And then these tractions, so they act on end cross sections. And you think of when we want to also insert torsion in the cylinder, then the two ends here have to be rotated in opposite direction, right. Okay. So, here is the cylinder, you rotate the cross sections in opposite direction. So, rotation of the right cross section relative to the left cross section. So, that is omega, which means you have to rotate each of the cross section by omega by 2, right, this by omega by 2 and the left also by omega by 2, but in opposite direction. So, that the relative rotation is omega. So, I am going to write here end to end cross sectional rotation that is omega. And usually if you want to do that, you will also have to apply torque, what is called torque, parallel to the axis of the cylinder. You have to apply some moment parallel to the axis of the cylinder in order to twist it. Okay. So, we not only apply what is called axial force at the two ends, we also have to apply torque, which we will denote by T, the torque T. So, you see the force and torque both are axial, then only you can apply the torsion. Okay. So, the force F is the axial force that we are applying and T is the torque. Okay. And then P, let us say P is the internal pressure. So, by applying axial force, torque and the internal pressure, we will generate extension, torsion and inflation in this hollow cylinder. And we want to see how does stress vary within the cylinder. So, see we are applying this at the end cross sections or through the inner surface of the cylinder, but we want to know how does this influence what is happening within the cylinder, what is the stress generated in the cylinder or what is the displacement that gets generated in the cylinder. Okay. And we want to solve it using cylindrical coordinate system. So, we have to find u r, u theta, u z, the three displacement components, and then the components of stress sigma r r, sigma theta theta, sigma z z, tau r theta, tau theta z, tau r z. Okay. So, the 6 stress components in the cylindrical coordinate system and the 3 displacements. Okay. So, let us see how we can solve it. Okay. So, before we start solving, we should think from physics what could be the form of displacement. Displacement in general u r, or let us say u, which is equal to u r E r plus u theta E theta plus u z E z. So, that is the displacement, and each of the components u r would be function of r theta z, the cylindrical coordinates. Likewise, u theta would also be a function of r theta z, and similarly u z in general would be a function of all the 3. Okay. But here we are talking about spatial deformation, extension, torsion, inflation, and we have to think of, can this displacement be more spatial, or let us say can the dependence on the 3 cylindrical coordinates, can some of them be gotten rid of. So, that is what we want to investigate here. So, the first thing that we would like to say is that when we apply this force, torque and pressure in the cylinder, then the deformation that happens is axisymmetric. By that I mean that the displacement components, for example, they are not functions of theta. You think of any theta here or here or here. So, you go by changing theta. So, on all those points you have the same displacement component. So, if the radius is fixed and z is fixed and only vary theta, then we say it is axisymmetric if the dependence on theta is not there. So, for each of the points we have the same displacement. Okay. So, that simply means that u r, u theta and u z, they all depend on just r and z, no dependence on theta, and that is due to axisymmetry. Think of, for example, if u r depends on theta, what can happen? So, let us look at the cross section of this cylinder. So, this is the cross section. And think of any circumferential line in this cross section, and what would be u r? U r would mean the radius of this line is going to change, right. If initially is a small r, then the final would be small r plus u r, correct. Now, suppose that u r depends on theta, then the change in radius is different for different theta. So, that would mean that the final circumferential line is no more circular, because for different theta you have different u r. So, the u r here is something else, whereas u r here is something else, right. So, we want to avoid that situation. So, we want to restrict to deformation which are symmetric. So, that means circular cross section remains circular. So, I will just write here, if u r depends on theta, then circular cross section will not remain circular. Okay. Likewise, you could think for u theta and u z, what happens if they depend on theta. So, the axisymmetry is basically going to be lost. Okay. All right, we would like to think more. What more restriction can we think of? Let us see, for example, u r. Now, u r is a function of r as well as z. So, what happens if u r is a function of z? So, let us think of again this cylinder. So, here is your cylinder, and we have this axis of the cylinder, and this is the radius. This is, for example, the outer radius r o, o for the outer. So, right now the outer radius is the same as you go along the axis, right. So, it is a simple cylinder, but if u r is a function of z. So, along the axis we have z, is not it. So, if u r is a function of z, then you see that after deformation this simple cylinder will no more remain a simple cylinder, it becomes a generalized cylinder, is not it. for example, it will become something like this. So, this is after deformation. Correct. So, we also do not want this situation. This is a bit complicated situation, but this actually happens in reality. So, suppose this is your cylinder and you are actually holding the end cross section rigidly. So, you do not let the end cross section to relax, and then if you pull it, you will see that the end cross section, since it is rigid, its radius will not change, but the cross sections within their radius is going to decrease due to Poisson's effect, right. When you stretch it, then due to Poisson's effect the radius will shrink, but because the end cross section you are holding it, so its radius is not going to shrink, it remains as it is, but cross sections here their radius is going to shrink, right. So, there will be non-uniformity in the radial shrinkage, and you will get exactly this kind of figure that we have here. So, this actually happens in reality, but then we want to think of a simpler situation where we are applying the force so that the end cross sections are also allowed to relax. If you allow the end cross section to also relax, then as you stretch the bar, each of the cross sections will then shrink by the same amount. Okay. And so, that would mean that we have axial homogeneity. Along the axis we have same thing, homogeneous. Okay. So, we want to restrict to the case of axial homogeneity. So, this means that u r of r z can then be thought of as u r simply of r, and this is due to axial homogeneity. Okay. Let us think of u z, for example. Can we further impose some restriction on u z? So, u z right now it is a function of both r and z. So, what does u z do? So, u z is the displacement in the z direction along the axis. So, think of a cross section. So, here is again cylinder, and think of a cross section here, a circular cross section. So, for this cross section, every point of this cross section has got same z value, right, because it is at some fixed axial location. So, every point of this cross section has got same z value, and if there is some u z, then this planar cross section will actually come out, right. If there is some u z, let us say positive u z, then this cross section it can actually bulge, is not it? It can become something like this. So, initially it is flat or planar, and afterwards it can bulge, or what is called it can become non-planar, or it can warp. Think of 2 points at 2 different radius, and if their u z is not the same, then after deformation they will not be on a plane, is not it. So, the final cross section will no more remain planar, it will get warped or it will become non-planar. So, we also want to avoid that situation, and that actually happens in reality also. If you nicely stretch or twist the bar, circular bar, then the cross section remains planar. Okay. All right. So, this again puts more restriction that u z, for example, is then only a function of z. And why is that happening? So, this means planar cross section remains planar or no warping. Okay. All right. So, we have gotten a lot of restrictions on u r and u z. Now, let us think about u theta. Okay. So, u theta, what can we say about u theta? First of all, again think of this cylinder and you are just stretching the cylinder. So, when you stretch the cylinder, it is going to generate axial displacement for different points and also radial displacement due to Poisson's effect, because the radius is going to shrink. So, there will be both u r and u z, but what about u theta? Will there be some u theta? So, we are simply stretching it. So, can a point change its theta coordinate? That is not really possible. It turns out if it is an isotropic cylinder, you are stretching it, then the points do not change their theta coordinate. Similarly, if you pressurize it, you pressurize it from within. So, when you pressurize, you are trying to change the radius of the cross section, and then due to Poisson's effect there will be axial shrinkage, right, because pressure is not direct thing. So, the radial strain is not the direct strain, and then the indirect is the axial strain. So, axial strain will come up now due to Poisson's effect. Okay. This is exactly opposite of applying axial force. So, this also generates only u r and u z, there is no u theta. But now, if you apply moment, torque, right. So, whenever the moment is parallel to the axis, we call it torque. So, if you apply torque, the cross sections are now undergoing rotation. So, when a cross section is rotating, so due to that rotation, some u theta is going to generate, is not it? So, if u theta is generating, that is due to the rotation of the cross section. If the cross section rotates, then only u theta generates. If the cross section does not rotate, then for the simpler case extension torsion inflation, there is no u theta. Okay. All right. So, let us think of, with this cross sectional rotation, what will be the mathematical formula for u theta. Okay. So, again we have this cross section, and think of any point in the cross section which has its radial coordinate r and the theta coordinate is theta. So, this point has got a small r, theta and z, and if the cross section rotates, let us say by angle alpha, then this point will rotate and come over here, right, and this angle is alpha. Of course, there would be some radial displacement also, due to which the radius of the point will change. But let us think of how much is u theta now. Okay. And also in this course, we are going to think of rotation which is very, very small. So, alpha is really small. So, that is the restriction of this course. So, in that case how much would be u theta? Can you recall what is u theta? U theta is the displacement in the theta direction. So, from this point that is the E theta. So, I want to talk about displacement in the theta direction. So, how much would that be? Can you see that if alpha is very small, then that arc will almost become a straight line and it will be actually along E theta, is not it? And how much is the length of the arc? That is simply alpha times r, is not it? So, what will be u theta then? That is alpha times r, is not it? So, u theta actually is alpha into the radius if alpha is very small. Okay. So, you see that u theta does not depend on theta again, and that we wanted because of axisymmetry. So, it only depends on r. You talk of different point with different theta, then the 2 points undergo same u theta. Now, how much would be alpha for a cross section? So, let us come back to our original figure, and what we had said is that the end cross sections they rotate by omega by 2 and omega by 2, is not it? So, that the total is omega. So, suppose that this rotation is linearly varying. Okay. So, from omega by 2 here in the negative. So, from negative omega by 2 it goes to omega by 2 in a linear fashion. Now, the total rotation is omega. So, what is the rate of change of angle? So, if it goes in a linear fashion, what is the rate of change of angular rotation of the cross section? It is simply the total rotation divided by the length of the axis, right, the length of the cylinder, which is L. So, the rate of change of rotation of the cross section would be omega by L. So, I can write here that the rate of change of rotation of cross section is omega by L, and this has got a name also. This is called twist. So, this is called twist. All right. Let us come back again. So, suppose that our origin is at the center of the cylinder. So, here is the origin. So, how much would be the rotation of the cross section which is at z equal to 0? So, this is the z equal to 0 cross section. So, that is z equal to 0 cross section, and rotation of this cross section will actually be 0, is not it? So, alpha of 0 is equal to 0. So, this cross section is z equal to L by 2, and for this cross section the alpha of L by 2 is equal to omega by 2, is not it? So, what would be alpha for any z? So, alpha for any z is simply the rate multiplied by z, is not it? So, we can write here that alpha for any cross section at z is the rate which is omega by L multiplied by z. Okay, so, we can put this alpha back in this formula for u theta, and then this would mean that u theta is equal to omega by L times r into z. Okay. All right. So, let us have a recap of the displacement. So, we have finally found out that u r is just a function of r, u theta is equal to omega by L into z into r, and u z is some function of z. So, notice that u theta is completely known here. So, it is fully known, but of course, omega is the unknown, some constant omega. So, when we apply some torque in the cylinder, it induces some omega, right, and that omega is unknown, which we will find out later on. So, torque T is known, and how much is the omega, that is the unknown. But except for the omega, u theta is completely known, the mathematical form of u theta is completely known, but u r and u z, they are still unknowns. We only know that u r is a function of r and u z is a function of z. Okay. Unknowns are u r, u z and omega. So, to find this, we have to use the stress equilibrium equation in cylindrical coordinate system, right. So, it has got stress in it. So, we would like to write stress in terms of strain through the constitutive relation, stress strain relationship, and finally, strain we have to write in terms of displacement. So, we have done all this in the last class. So, the first goal would be now to find out the strain matrix in the cylindrical coordinate system. Okay. The strain matrix epsilon in r theta z coordinate system. So, we know that it is a big matrix. What are the diagonal components? If you recall, the first one, the 1 is del u r by del r, but here u r is only a function of r. So, it simply becomes u r prime. This 2 component, if you recall, that is 1 over r del u theta by del theta plus u r by r, but because u theta is not a function of theta. So, we simply have u r by r. Okay. So, the hoop strain is u r by r, and finally, the axial strain, that is del u z by del z. So, it becomes u z prime, because we know that u z only depends on z. So, it is u z prime. Okay, let us now think of the shear strains. So, what is epsilon r theta? So, epsilon r theta, we know from the formula that this is 1 over r del u r over del theta minus u theta plus del u theta over del r and half of it. Right. Now, del u r over del theta is 0, because u r does not depend on theta. So, this becomes half of del u theta over del r minus u theta over r. So, let us plug in the formula for u theta here. So, we know that u theta is omega by L into Z into r. So, that means del u theta by del r is omega by L into Z, which is also equal to u theta by r, right. So, when we substitute this here, we then see that epsilon r theta is actually 0. So, this means epsilon r theta is 0. So, for this spatial deformation, there is no shear strain in r theta plane. So, gamma r theta, which is twice of epsilon r theta, is 0. So, we can write 0 here, all right. Now, talk about epsilon r z. So, that is half of del u r over del z plus del u z over del r, and this is again 0, because u r is only a function of r and u z is only a function of z. So, we can come back to this matrix and write 0 here. Okay, now, what about epsilon theta z? So, epsilon theta z, that is half of del u theta over del z plus 1 over r del u z by del theta. But u z is only a function of z. So, this is gone and we simply have half of del u theta by del z, and which from the formula for u theta simply becomes omega r over 2 L. Okay. So, we can write here omega r by 2 L. Okay, very good. So, we have gotten the strain matrix. Now, the next thing would be to find out the stress matrix, right, the different components of stress. So, we can use the stress strain relation in terms of the Lame's constant, because strain is known here and we want to get stress. So, the relation using Lame's constant would be useful, right. So, that tells us that sigma I j, if you can recall, was lambda times delta I j times epsilon k k, we have summation over k. So, that is the trace of epsilon plus 2 mu into epsilon I j, all right. So, what would then be sigma r r? So, that is lambda times trace of the strain matrix. So, the trace is simply the sum of the diagonals, which is u r prime plus u r by r plus u z prime plus 2 mu times u r prime, right, because that is epsilon r r. Likewise, sigma theta theta is lambda times u r prime plus u r by r plus u z prime plus 2 mu epsilon theta theta, which is u r over r. Then sigma z z is then lambda times u r prime plus u r by r plus u z prime plus 2 mu into u z prime, and then tau r theta is g times gamma r theta, which is equal to 0, then tau r z is equal to g times gamma r z, which is also equal to 0, and finally tau theta z, that is equal to g times gamma theta z, but that is not 0 and it is equal to 2 g into epsilon theta z, and that is equal to g into omega r over L. Okay, so, we have gotten the stress components in terms of displacement, is not it, u r, u z and the omega. So, we simply have to plug in this in the stress equilibrium equation and solve it to get the displacement, right. So, let us proceed further. So, let us write down the stress equilibrium equation which we have derived. So, it is del sigma r r over del r plus 1 over r del tau r theta over del theta plus del tau r z over del z plus sigma r r minus sigma theta theta over r plus the body force B r and equal to rho times acceleration. But suppose we are talking about statics here. So, we apply force and then body deforms and comes to rest. So, we are talking about static configuration, there is no dynamics, there is no acceleration then. So, the right hand side would then be 0, is not it? So, it becomes 0. Okay, then the next equation is del tau theta r over del r plus 1 by r del sigma theta theta over del theta plus del tau theta z over del z. Then we have the unusual term 2 times tau r theta over r plus the body force in theta direction, and that is equal to 0. And finally, the z equation, which is del tau z r over del r plus 1 by r del tau z theta over del theta plus del sigma z z over del z plus the unusual term, which is tau r z over r plus body force in the z direction, and that is equal to 0. Okay. So, that is the equation. Now, what are the things which we can say is directly 0? You see, from our strain matrix and then we also found out the stress matrix, we can see that tau r theta and tau r z are completely 0. And what about the non-zero stress components? So, they are only functions of r and z, none of them are functions of theta. See, that again happened because we started with axisymmetric displacement. Therefore, strain matrix also becomes axisymmetric, and finally, the stress matrix also becomes axisymmetric. So, whenever you have axisymmetric deformation, then displacement, strain, stress, they all become axisymmetric, right. So, if we come back to our equation again, then wherever we have derivative with respect to theta, they are all going to be 0, right. So, we can say this is 0, this is 0, this is also 0. And then what about tau theta r? So, we know that that is 0. So, its derivative is also 0, then this term is also 0, right. Then tau r z is also 0. So, this also becomes 0. So, you see there are lots of cancellations, and this all happened due to axisymmetry. There is no dependence on theta. If we were using E1, E2, E3 coordinate system, then there is no theta present there. What we have there is x 1, x 2, x 3, x, y, z. There is no theta coordinate. So, it will not be straightforward to use axis symmetry there, and there is no direct cancellation of any terms in the stress equation sigma x x, sigma y y, sigma z z. We can't say that del sigma x x by del x is 0, or del sigma x x by del y is 0, or del sigma y y by del y is 0, or del sigma z z by del y is 0. So, because there is no theta, so there is no cancellation there. So, that is the advantage of using cylindrical coordinate system. Whenever you have axis symmetry, of course, the cylindrical coordinate system is a lot useful, because you see lot of cancellations. Okay. All right. What more can we say? What about del tau theta z over del z? So, what about this term? So, look for the expression for tau theta z. So, tau theta z, so this has no z dependence, it is only a function of r. So, del tau theta z by del z would also be automatically 0. So, this is also 0. So, you see lots of cancellations. Now, let us talk about the body force. What will be B r, B theta, B z? If we have the cylinder, suppose it is in the vacuum or in the free space where there is no gravity or there is no body force, then B r, B theta, B z are simply 0, right. So, let me draw the cylinder. If the cylinder is like this and the gravity is acting downward, then what can we say about B r, B theta and B z? So, for different theta we will have different B r and B theta. So, we will have to resolve this g along E r and E theta. So, we will get perhaps B r as rho g sin theta and B theta as rho g cos theta. So, depending on where the theta is starting from. So, B r would be something like rho g cos theta and B theta would be rho g sin theta. Basically, it will have cos and sine or sine and cos, okay, depending on where the theta is starting from. So, this is one situation. In the other situation, if we have this cylinder again, and g is acting in the z direction. So, that means the cylinder is vertical and g is then along the axis in the z direction. So, in that case B r and B theta will both be 0 and B z would be equal to rho times g. Okay. There is another situation. Think of a cylinder which is rotating about its axis. So, it is rotating about its axis with a constant angular velocity. So, you know, we always have shafts in various machine. If you go to lathe machine, it has got a shaft which is constantly rotating. Look at all kinds of motors. In all motors, we have some rotor or shaft which is constantly rotating. In jet engine, we have the rotor which is constantly rotating, right. So, when a rotor is constantly rotating, what is the acceleration of any point in the rotor? So, that is simply it has got centripetal acceleration, right. Remember from the first year engineering mechanics, it has centripetal acceleration which points towards the center, and in the cylindrical coordinate system will be along negative ER, it is towards the center. And what is the value of the acceleration? That is rho times omega square r. So, the centripetal acceleration is omega square r, right. So, in that case, so I can write here again, in case the shaft is rotating, then acceleration in the radial direction, it will be equal to minus of omega square r. So, we only have acceleration in the radial direction, and a theta is then 0 and a z is also equal to 0, but the body force it is not there if you neglect gravity. But at the same time, if we sit in the frame of rotating shaft, so if we sit in a frame which is rotating with this shaft, so it is a rotating frame, it is not an inertial frame, it is a non inertial frame. So, in that frame if you want to apply Newton's second law, then we have to apply pseudo force, right. And then in that frame the shaft will not be rotating, shaft will be static, but then the pseudo force has to be applied, is not it. So, there instead of acceleration we will have body force, centrifugal force, pseudo force would be like the centrifugal force. So, here it is centripetal acceleration, centripetal acceleration, but in the frame rotating with shaft, A r, A theta, A z are all 0, because we are in the frame of the shaft. So, we will not see the shaft rotating. So, it will be in statics. So, in this frame we have to apply pseudo force or centrifugal. When we do linear momentum balance, and then the centrifugal force will be radially outward, okay, and that is going to act on every particle of the shaft. So, it acts like a body force. So, in the inertial frame there is no body force, but every particle is accelerating, but in the non inertial frame of the shaft there is no acceleration, but then every particle has got some pseudo force which is like a body force. So, in this frame we will have B r equal to rho times omega square r, and B theta equal to B z will be equal to 0. So, the radial equation for example would become del sigma r r over del r plus sigma r r minus sigma theta theta over r plus B r, which is rho omega square r equal to 0. So, this is for a rotating shaft. Okay. So, this was just a side discussion, but coming back to our original problem where we are applying some axial force and torque and pressure. This cylinder is not rotating, and let us also suppose that there is no gravity. or there is no body force. So, in that case the equations that we have, so coming back to this equation, each of the body force components will also become 0. Okay. So, you see what has happened now. So, of course, this is also 0. The theta equation gets trivially satisfied. All the components in theta equation are 0. So, theta equation is automatically satisfied. That is again the outcome of axisymmetry. So, theta equation is automatically satisfied because u theta is known to us for this kind of deformation, axisymmetric deformation. Therefore, theta equation gets automatically satisfied. All right. So, let us write down the final equations. So, the final equation for extension torsion deformation so we have del sigma r r over del r plus sigma r r minus sigma theta theta over r equal to 0, and theta equation is completely 0, but the last one is del sigma z z over del z, that is equal to 0. So, this is a reduced equation, and we would solve this to obtain all the stress components. So, we want to obtain u r, u z, omega and the stress components sigma r r, sigma theta theta, sigma z z and tau theta z, the 4 stress components. Okay. So, I will stop here and we will continue from here in the next class. Thank you.